Alright guys, so what we're going to talk about tonight is thermochemistry, and obviously as the name would imply, we're going to talk about heat and energy considerations and how this interplays with the matter that we tend to think is sort of the focus of chemistry. And all I really want to hit on in this first video for Thermochem is really just to talk about what the terminology is, maybe clear up some misconceptions and give you the sort of the foundation there so that we can then jump off into all the math and stuff that we're going to do a little bit later. So if we're talking about energy, if we're talking about heat, then we need to know what energy is. And energy is one of these great things. I mean, no one can really give you a real firm definition for it. If you talk to some upper level PhD in physics, they might sort of give you some hand-waving answers. But the fact of the matter is that it's really tough to nail down a real definition of what it is. But essentially, our textbook answer is usually that it's the capacity to do work or to produce heat. And this is probably the definition that you learned in elementary or middle school. In physics, we're usually a lot more concerned with the ability to do work. If you remember, work is basically applying a force over a distance. Something has to move in order to do work in the scientific sense. In chemistry, we're going to tend to be a little bit more worried about the heat aspect, whether we're producing or absorbing heat, and what's going on with the energy, with the heat part of the energy there. There's a little bit of the work part that goes into it as well, particularly when we're talking about expanding volumes. But typically speaking, we're a lot more concerned with just the heat part. We're going to just sort of start off and just remind you of this idea that you've probably had hammered in your head since, I don't know, second or third grade, which is the idea of the law of conservation of energy. And the idea, obviously, is that energy cannot be created or destroyed. And essentially, this is basically a rephrasing of what we call the first law of thermodynamics, which obviously sounds a little bit more heavier than the law of conservation of energy. But essentially it just means that the energy in the universe is constant, that there's no creating or destroying of energy, that it's always constant, and that what is happening then is that energy is converting from one form to another, or maybe it's moving from place to place, but the sum total of all of the energy is always constant. Now, these are some of the forms of energy that, we'll deal with all the time. In physics, you probably talk a lot about potential energy, particularly gravitational potential energy. So you probably used, some equations that probably seem pretty familiar to you. You probably used something like potential energy is equal to, that was an equal sign, is equal to mgh equal. Okay, you probably use something like that. That's gravitational potential energy. So the higher something up is up, and the more massive it is, the more energy it's going to have. That's probably pretty familiar to you guys that took physics or PWC before. We've got kinetic energy, and of course we know that formula. We've used that a little bit in chemistry last year, and we'll use it a little bit again this year. Kinetic energy is obviously going to be then related in some ways to thermal energy. Thermal energy usually means we're talking about heat, so you think about friction, or you think about heat being given off, and that's going to be thermal energy. Chemical energy, sometimes you hear this called chemical potential energy. So this is the energy that's actually stored in the bonds between the chemicals, between the atoms in our molecules. And obviously that's going to be super important to us because we're doing chemistry, and so a lot of what we're going to be concerned with there, what's the energy in the bonds, how much is going to be released if we break those bonds, or how much, if we reform the bonds, what happens to all of that energy. And of course, we've got stuff like nuclear energy as well. So there's a lot of energy tied up in those forces that hold the nucleus together, and that's why, of course, if we can split an atom and release that energy in the context of like nuclear fission, or if we could condense it down to basically force two nuclei together in the case of fusion, enormous amounts of energy are released. And so we can, sort of dream up some scenarios where we'd use these sorts of things. We've got a car on top of the hill, and it's traveling down the hill, and its potential energy is converted to kinetic energy as it goes down the hill. You hit the brakes, and some of that is then converted into heat energy, into thermal energy. Obviously, the car is driven by chemical energy, the combustion of those chemicals that are in the tank, or maybe it's just some super awesome future car, and it's powered by nuclear energy. Who knows? This goes back to this idea that we looked at in the last section, which was basically that it's converted typically from one form to another, that we're not really creating or destroying any energy in the things we do, but we're just moving it from one place to another, or converting it from one form to another. So this is actually sort of the formula for that first law of thermodynamics. The energy of the universe is equal to the energy of the SYS plus the energy of the SURR. And what the heck does that mean? Well, essentially, the SYS there means the system, and then the SURR means the surroundings. And so basically, the energy of the universe is equal to the energy of the system plus the surroundings. So what does that mean? The system is just the area that we want to focus on, that we want to concentrate on. And here's the beauty of that. We get to define that. And so if we're doing some chemistry in the lab, and we might decide that we're going to define our system as, this beaker that we're putting chemicals into, or that we're adding something to, and we're going to measure the heat. That's going to be our system. Okay? And then everything else in the universe is the surroundings. And so what that means is that if I put energy into the system and the system's gaining energy, then the surroundings has to be losing energy in order to keep the energy of the universe constant. And we'll get a little bit more into the math of this a little bit later. So, a couple other definitions of things that are sort of hard to grasp, because that's what energy, we said at the very beginning that the definition of energy is hard, and so most of the definitions associated with it can be a little bit difficult. So we've talked about temperature before when we talked about kinetic energy, and we said, or kinetic theory. And we essentially said that temperature is the measure of the average kinetic energy of the particles in a substance. So particles are always moving around. Remember, the only time that they stop moving around is if we get to absolute zero. That's a theoretical state anyway. We've never actually completely gotten there. And so for us, particles are always moving. And so temperature is basically our way to sort of measure the average kinetic energy of a given system. So how fast are those particles moving? Remember that kinetic energy, that this formula here is 1/2 mass times velocity squared. And so basically that means if you're measuring a system, and like when we talked about gases in the last unit, if we're measuring the temperature of a mixture of gases, the smaller gases are going to have to be moving much faster if they've got the same temperature, if they've got the same kinetic energy. And the larger ones are going to be moving much slower, so that kinetic energy and therefore the temperature is evened out between those different gases. So that was temperature. Probably one of the most misquoted or misdone definitions in all of Thermochem, or all thermodynamics really, is that of heat. And heat has to be a transfer of energy. Okay, and what I want to make really clear here is that heat is not a property of a substance. We have properties of a substance that are related to heat. We have like specific heat, or specific heat capacity. But heat itself is not a property of a substance. You can't, grab a substance and say it has this much heat in it. Okay, heat is temperature differences between two things and energy flowing between those two things. And so, as an example, if we were going to do, say, a calorimetry experiment, we'll talk more about calorimetry in future videos and in the lab. But if I've got a beaker full of water and it's at 25 degrees Celsius, and I say heat up a piece of metal to 50 degrees Celsius, and then I put it in the water, then what happens is that I get a flow of energy from the metal that I'm doing into the water. Okay, and eventually they're going to reach a point of thermal equilibrium. They're going to reach a point where the temperature of the metal and the temperature of the water are essentially the same. But while that's going on, there's a transfer of energy from the hotter object to the colder object, and therefore there is heat. There is transfer of energy between those two things. So that's all well and good. And how that relates to the system, a couple of terms that go along with that we will hopefully remember from Chem 1. If the heat energy is flowing into the system, then that is what we say is an endothermic situation. And then if energy is flowing out of the system, that is what we call an exothermic situation. If you remember, we actually had a couple of particular signs that were associated with that. So if we had an endothermic heat, then that had a positive sign. And if we had an endothermic heat, that had a negative sign. Because in this case, over here with endothermic, we're losing energy out of the system. And in exothermic, we're losing energy. In endothermic, the system, okay, the stuff in the beaker here for us, is gaining energy. Exothermic, it's losing, so that's negative. Okay? So that leads us to sort of our last little piece of terminology here for us. This is one of the easier equations in chemistry, but it might look a little weird. Remember that anytime you see this little delta here, that just means change in. And so we just sort of real briefly need to define what the terms are here. The capital E, as you might expect, is energy, and so that's good. Usually what we're talking about in terms of chemistry is we're talking about the internal energy of the system. So Beakers are system, the energy inside of that system, that's its internal energy, okay? And we can really only measure that in change in. We'll see that energy isn't really something that you can just measure absolutely out of an object. What we can actually really only measure is the change in energy from situation to situation. So the W over here is work, and again, we're going to see that that's going to fall out of our equations a whole lot in chemistry. We're not going to do a whole lot of work except in a few specific situations, usually related to gas laws. And then the other one here, yeah, guess what the Q is? The Q is heat. And I know we talked about that before in Chem 1. We did calorimetry stuff, and we'll do that again this year. But, hey, I don't know what to tell you. Heat is Q. We're going to see that H actually has a different meaning here in a little bit. It is related to heat, but it is not directly heat. So just remember those terms. And all of this, by the way, the units on all of this is capital. What we're usually going to use for our units anyway is going to be capital J for joules. Okay. We will occasionally maybe see some cal for calories, but typically we like to stick with joules when we're doing SI type stuff for us. Okay, so that's just a few real quick hit definitions. We're obviously going to dive a lot further into this and do some of the math, talk a little bit more about the terminology. In our next video, we'll talk about state functions, and we'll talk about what we're really going to use in place of heat most of the time, which is a weird little quirky term called enthalpy. But hopefully that gave you a good grasp on what the basic definitions are for us. Thanks, guys.